Kakerlaken. Okay, so we are starting example 4. We're just going to start from scratch. We're trying to find the average rate of change of a function that changes at a variable rate. Namely, not a what? Line, right? Lines change at constant rates. So we have this function, x minus 4 quantity squared. That's a parabola that has moved to the right 4. We sketched that yesterday. There it is. So on part A, we are trying to find the average rate of change on the x interval from 2 to 4. So 2 is our starting x value. 4 is our ending x value. I drew that yesterday. This might be what it looks like. So we're starting at 2, which I'll use pink here today. It is October. And then this graph is actually going down towards 0 and stopping at 4. So the pink path is the path it actually took. So notice that because it's curved, the rate at which it approached 4.0 varied. But we can't find the rate of change at any single point in time because we don't know calculus. So the best we could do is to find over the interval from 2 to 4 its average rate of change. Okay? And that turns into then geometrically finding the slope of that green line, which we call the what line? Secant line. Good. So the slope then of that secant line is the exact same thing as the average rate of change, which I'll abbreviate ROC, on that interval. So we kind of mentioned, Newton and Leibniz and even Galileo yesterday. They are the exact same thing. From a graphical perspective, the slope of the secant line, that's more the Leibnizian perspective. And the average rate of change, that's talking about how real quantities in real life change, like positions or temperatures. That's the Newtonian and Galilean perspective. So how are we going to set that up? Well, some people get confused. They think 2.4 is an ordered pair. Is it? No, it has brackets, not parentheses. But even if that had parentheses around it, in the context of what I'm asking, it would still be an open interval, not a closed interval. So we're going to go ahead and say that the average rate of change, we'll label it, you can abbreviate that ROC, equals, and it's the what? DQ, right? What does that stand for? Disqualification, Dairy Queen, difference quotient. Good. So you want to get in the habit of doing final minus initial. So we're going to set that up as f of 4, that's the ending x value, minus f of 2, that's the beginning x value, all over the change in the corresponding x. So that was just your delta y over delta x. That's what I'm going to expect to see on a quiz, okay? That's your difference quotient. Now, you did learn in algebra that it doesn't matter the order. So if you did f of 2 minus f of 4 all over 2 minus 4, you would get the exact same answer, okay? You would get the exact same answer. But I don't want you to do it this way because when we start looking at applications, if you do final minus initial, then what the numerator becomes is meaningful. It becomes something called displacement, which is a vector. All right, so if you do initial minus final, you're going to end up with the wrong sign. So get in the habit of doing right minus left, big minus small, top minus bottom, okay? So now that we have it set up, how do we find f of 4 and f of 2? Yeah, plug it into the equation. There it is. What is f of 4? What do you get when you plug in f of 4? You get 4 minus 4 is 0. 0 squared is 0. Okay, now f of 2, when you plug in a 2, 2 minus 4 is negative 2. Negative 2 squared, positive 4. So we get 0 minus 4 all over 4 minus 2. Now, I didn't have to put 4 minus 2 like that in the denominator, but that's another difference quotient. Let me go ahead and just call that 2. And now I have negative 4 over 2, and I'm simplifying, and I get negative 2. And that's our answer, negative 2. So what that means then is on average, to get from the point on the left, the pink point on the left, to the pink point on the right, on average, I go down 2, right 1, down 2, right 1. Okay? But is that how I actually got there? No. I got there at variable rates. So it's kind of the same analogy that if you went from here to San Antonio and you averaged 60 miles an hour, that doesn't necessarily mean you're going 60 miles an hour the entire time. Okay? Let's do the next one. This is another way for me to give you an interval. Instead of interval notation, this is inequality notation. This is the interval from 5 to 8. This is what I had y'all do in the warm-up. So let's go ahead and set it up together. That would be average rate of change. Or you could even say, let's do it like this. M with a subscript of secant. What would that mean? What does M stand for? Slope, right? Slope, right? If you had to choose a letter to represent slope, M is the natural choice. Right? Good. Yeah. Because if you say slope, you hear that M sound come through, don't you? Slope. Why M for slope? Let's analyze that. I don't know if y'all know why M for slope. Anyone know why M for slope? That should have been like in Algebra 1 when you first met slope and you called it M. You're like, why do we call it M and not, I don't know, S? You never called it M? Y equals mx plus b? That doesn't... Yeah, when you have y equals mx plus b, m is the slope and b is the y-intercept. Yeah, okay. M is for mountain. Mountain. And what do you do with a mountain? You climb it because it's there, right? So it's from the French verb monter, which I think in Spanish is very similar, monter, which means to climb or to mount, essentially. To mount a horse? Montar is just a horse? But that's in Spanish? So maybe in France, monter, instead of montar, is to mount a horse and take it to the top of a mountain. Maybe in France, that's what it is. So anyway, for whatever the reason, maybe the connotation of how it's used has changed, but that's where it comes from. It comes from to mount a mountain, whether you're on foot or on a horse. Okay, so then we're going to set it up as the final, which is f of 8 minus f of 5. If we were talking about the function f representing positions, then f of 8 would be my final position minus f of 5 would be my initial position. We would call that quantity displacement, and we modeled that yesterday. 2 to the right, 2 to the left. My distance traveled was 4, but my displacement was 0. So that gives you your displacement of your y values all over the change in the corresponding x values. So again, there's your difference quotient. When we quiz tomorrow, that's going to earn a check. And now all we have to do is to evaluate it. How do we evaluate f of 8? Plug it in. 8 minus 4 is 4. 4 squared is 16 minus f of 5. This is so much fun, plugging things in, right? 5 minus 4, 1. 1 squared is 1. Now, because we've already shown the difference quotient, I can just call the denominator 8 minus 5 is 3. And so I get 15 thirds, which turns into 5. Yeah. So I didn't graph that, but it would look something like this. If I started at 5 and I ended up at 8, here's where I'm starting, here's where I'm finishing. Notice I follow the blue path. So if you notice what's happening to the rate of change as I move to the right, is it increasing or decreasing? Increasing, right? The graph as we move to the right is getting whatter? Steeper, right? So if you talk about rate of change of position, we call that velocity. The velocity of the graph, which could be used to describe how fast it's going up. Would you be okay with that? The velocity of the graph, describing how fast it's moving upward, is increasing. So it's starting off kind of slow, and as we move to the right, it's getting steeper. So it's moving upward faster with a greater velocity. We don't know what those velocities are, but here's what we do know. We know that the average velocity of the graph moving upward is 5. So if this graph was like in a car, it would have its cruise control on at 5, and it would follow the path of the green line, and it would get to that same point at x equals 8 at the exact same time as the guy in the blue car who's not using cruise control. He starts off slower, and the guy on cruise control 5 is passing him up, but then this guy speeds up, and boom, they get to the finish line at the exact same time. One of them is getting there at a constant rate, the other one's getting there at a variable rate, okay? When all we have is a beginning point and an end point, all we can find is the average rate of change between them. So up 5 over 1, up 5 over 1, up 5 over 1. All right, last one, you do by yourself. Notation, notation, notation. No notation? No points. All right, no notation, no points. Make sure you label it average ROC or M subscript secant. I don't know. I haven't done it yet. Yeah. I mean, I'm trusting your math, right? Right? And let's see. I'll sketch it while y'all are doing that. We're going from -1 to 9, so -1 could be right around here, and 9 would be somewhere over here. I'll move my 8. So it would be right around here. It would be 9. And so the secant line looks like that. Yeah. Graphs can be very misleading. If you sketch a graph, all we're concerned about is really where's the vertex and does it open up or down. The aperture of the graph, how steep or shallow it is, I'm just guessing, right? But the calculations that you're doing, they don't lie. All right, so let's see what y'all did here. Hopefully you went average, and you could abbreviate this ROC, or you could put subsecant. Either one, right? Like Campbell's soup. It's Good, right? Yeah, I don't know if that's still their motto. Yeah, okay, good. Yeah. Why change something that's working? I want some good soup. Oh, Campbell's is good. I'll buy that. F of 9 minus f of -1 all over 9 minus -1. Is that right? Very good. Your brain can kind of mess with you a little bit because you know you have to go 9 minus -1. And so when you write it down, your brain can say, hey, there's already a negative there. How convenient. I guess I don't need the other one. That's not correct, okay? You're subtracting a negative number. So in terms of getting credit for a difference quotient, you can get credit if you have f of 9 minus f of -1 over 9 minus -1, or f of 9 minus f of -1 over 9 plus 1. That would still be okay. Because remember, addition and subtraction are just two sides of the exact same coin. So when we say a difference quotient, it could actually be an addition quotient. Not a problem. Okay? So let's go ahead and evaluate it. F of 9, that's going to be, and again, notice I'm working straight down with an equal sign. That's 9 minus 4, which is 5. 5 squared is 25. And then f of -1, you get -1 minus 4 is -5. -5 squared is 25. All over 10. So I get 0 over 10, which is DNE. 0 or DNE? I always forget. That's 0, right? Remember, non-zero over 0 is infinity, or negative infinity, undefined, DNE. It's an average rate of change. Yeah, so here, let me draw it on the graph. At -1, I plot it, and at 9, I plot it, and it turns out, and if I would have done it according to my graph, my green line would have had a lot of pitch to it, because I already put 8 right here, so that's why graphs can be misleading. But then the calculations tell the true story. It just so happens that the y values are the same, so the average rate of change is 0. So yesterday, remember, I went 2 steps to y'all's right, 2 steps to y'all's left. My displacement was 0. What was my average rate of change during that dance? My average rate of change was 0, right? Because I was right back where I started. If you went from here to San Antonio, and then you turned right around and came back because you realized you forgot your car keys. What? What would be your average rate of change on that trip? 0. But does that mean that you were going 0 the whole time? No. Maybe if you forgot your car keys, it would be 0 the whole time because you never got out of the driveway. If they're close by. Is San Antonio close enough to New Braunfels that it would start? I don't know. Maybe so. I could just see y'all like walking all the way to San Antonio, and you get there and you're like, crap, I forgot my car keys. So you walk all the way back, and you're like, here's my car keys. You're like, hey, since I have car keys, let's just drive this time. Right? Okay. Whatever. Because you Ubered home, I guess. All right, sweet. So yes, the average rate of change is 0. The slope of the secant line is 0, which means the secant line is what type of line? Horizontal line. Yeah. Horizontal lines are very, very important in calculus, okay? Because their rate of change is 0. They're very important in calculus. Okay, so I think you can do that on the quiz tomorrow, right? Show the difference quotient, plug in carefully, and evaluate. Just keep your equal signs all the way down, or you can even write average ROC each line. But if not, keep your equal signs lined up. All right, comments or questions on that? All right, that was really a Leibnizian perspective. We were talking about the average change of y values. It's kind of boring, right? But what can we measure on y-axes? Pretty much anything. So here is example 5. When a pre-calculus textbook, now we got to stop right there, right? Textbook? What is a textbook? Anyone ever seen one? Your grandma's house. There you go. Or a museum, perhaps. Right? We used to have these things called textbooks. And they were kind of like iPads, but they were a little bit heavier. And you just carried them around. There's one. There's one. Yeah. And what was cool is that now you have split screen capability on your iPad, so you could view 2 digital textbooks, but you could actually set out 10 or 12 textbooks in front of you, and you can look at all of them kind of at the same time. It was really nice. And then you'd put them in your rucksack, and then you trekked to school, and you got back injuries and neck injuries, but you grew strong with your legs from toting these things around. So that's what a textbook is, all right? Let's say it's dropped from the top of a tall tower, all right? So students who used to struggle in math, not y'all don't struggle in math anymore, but kids used to struggle in math back when the teaching wasn't as good, and they would do poorly on tests and stuff, and so they were filled with angst and anger, and they had to take it out on something, right? And crime was still crime, so what did they do? They took it out on their textbook, kind of as a catharsis, as a release, okay? Stupid textbook. So they took it to the top of a tall tower with the intention of doing what? Not studying up there, yeah, but dropping it, okay? So a book is dropped. Now, we're not super angry. We're not throwing it down to the ground or throwing it into the air from that tower. We're simply just holding it there at the top of the tower and letting it go. And let it go. And when we let the book go, so does all of our angst and all of our anger. And then the Frozen song comes into mind. Let it go, let it go. All right, so after t seconds, the height above ground, or the distance that has fallen, the distance that has fallen is given by d of t equals 16t squared. That's a real equation, by the way. That's how it works near the surface of the Earth. If you get a really tall tower and you're too far away from the surface of the Earth, rules change, okay? But if you're within the atmosphere, that should work. Find the book's average rate of change, or the average speed, average rate of change of position, non-directional is speed, over the following intervals. Okay, well, is this any different from what we just did? No, it's the average rate of change now, but not the average rate of change of the y values. It's the average rate of change of position, which we can measure in feet, divided by the change in time, which we measure in seconds. So what would the units be now? Now that we have units on the y and x axis, it would be feet per second. Yeah, and feet per second is velocity. Oh, sweet. And now we are now in the Newtonian world, okay? So here's what we could say right now. The average rate of change of position, whether you're talking about horizontal position or height, is what we call average velocity. And the units tell us that. Wow, look at his position change with respect to time. He is covering many feet in a few seconds. He is fast. He has great velocity. Okay? So let's go ahead and figure out then, turns into the average velocity. So instead of saying average rate of change here, we'll say average velocity. And you can abbreviate that average vel. It equals, now not f of 5, but what's our function? D, all right? So we're going to use d of 5 minus d of 1, all over 5 minus 1. Okay, now we're not concerned with direction here. The book is falling, so its velocity is going to be negative because its position is decreasing. But we're not worried about vectors right now. We're just getting speed quantities. So d of 5 is going to be 16 times 5 squared, which is 25, minus d of 1 is 16 times 1 squared, which is 1, all over 5 minus 1 is 4. So there's the difference quotient on the first line, labeled as average velocity. You'll get credit for that. I'll probably give you credit for that too, right? Just kind of thinking about a quiz tomorrow. Now, you're not going to have a calculator tomorrow in the quiz, but I will expect you to simplify. So there's a couple ways to do it. You can go 16 times 25. You can go off to the side, 16 times 25. I love stacked double-digit multiplication, right? You haven't done that in a while, but that's still legal, right? Is it shameful to have to go off to the side and do stuff like that? Absolutely not, right? It's actually fun. It takes you back to the glorious days of mathematical yesteryear. But is there a smarter way to do that? This is pre-AP after all. We shouldn't just like come in with sledgehammers and just start slinging them around mindlessly, right? Like an ogre. We're sharp. We're astute. We're clever. We look before we leap, right? We're thinkers. So what would be an easier way possibly to evaluate that? Divide out the 4 from 16. Yes, which 16? This one? Oops, not that one. Would I do this and say that's a 1 and that's a 4? Would that work? No. We've had that conversation many times this year. We can only divide out common factors. So you were right on. We just need to factor out the 16 first. So that gives us 25 minus 1. And because we have now the spirit of going small before we go big, some of y'all have that number, 16 times 25 minus 16. Some of y'all have that number. But then you're going to have to go off to the side and probably do old school division, right? Which is fine. There's fun in that, right? Like on a Sunday afternoon, you take the scenic route just to enjoy the beauty. So if you're doing this problem on a Sunday afternoon, maybe go ahead and multiply 16 by 25, subtract 16, go off to the side and divide by 4. But we're not on a Sunday afternoon. It's actually a Tuesday morning. Thursday morning, actually. It's Thursday already. Yes. I factored the 16 out of both terms. Let's try it again. Let's distribute. Let's see what happens when we distribute. If I distribute, I get 16 times 25, which is right here. Minus, if I distribute, I get 16 times 1, which is what? 16. Okay, what if this were like x times 25 minus x? Y'all would know easily then to factor the x out and call it 25 minus 1, wouldn't y'all? Okay, what if it was 25x minus x? Would you then say then you could factor out the x and say it's 25 minus 1? That's all we're doing, folks, except instead of x, we actually have something that x usually represents a hope and a dream? No, a number. A number, right? I have a common factor of 16 in both terms. So I can factor or divide it out from both terms. So I'll put the 16 on the outside. And what do I get when I factor a 16 out of a 16 times 25? I get 25. And what do I get when I factor or divide a 16 out of itself? I get 1. So you have to start looking for things like that. It works with numbers, not just variables. And again, if you're still not convinced, just mentally redistribute it, and you'll see that I get that line above. Okay? Now that it is factored out, we can actually divide before we multiply. What's 16 divided by 4? 4. So I'm left with 4 times 25 minus 1 is 24. And is that a much easier number to work with? Yes. 4 times 4 is 16. Carry the 1. 4 times 2 is 8 plus 1 is 9. You get 96. Didn't break a sweat. Okay? Now, on any application, on our final answer, you need to make sure we put units. What are the units here if we're measuring the height of the book in feet and time in seconds? What are the units? Feet per second, right. And if you don't know, just include units in your calculation. We're measuring distance in feet. Time is measured in seconds. Feet divided by seconds is feet per second. All right. So let's go ahead and write a sentence. Okay. Here's your writing task of the day. You always want to start when you're asked to interpret this, and I might ask you to interpret it. You want to always start with an introductory adverbial clause. Y'all remember what those are? That references the interval of time. So how about this? It says during the first, what? After t seconds. So this would be on the interval from 1 to 5. So here's what you would say. We're going to do it like an engineer, not like an English poet, okay? From t equals 1 second to t equals 5 seconds, comma. There's your introductory adverbial clause referencing the interval of time. Now, English majors can kind of improve on that saying, during the 4-second interval from 1 to 5 seconds, right? We're not going to do that. We're just going to say, hey, from t equals 1 second to t equals 5 seconds, comma, the average speed of the falling, parentheses, and crying, textbook is or was. Is it happening now or did it happen in the past? That doesn't really matter. We'll just say is 96 feet per second. Now, if we were looking at velocity, it would be negative 96 as an average velocity. Negative means that the position or the height is decreasing. Okay? Now, does that mean that during that 4-second interval from 1 to 5, the book was falling 96 feet per second the whole time? Is that how gravity works? Everything falls at a constant rate? No, what happens? It speeds up, right? Little g gets involved. And by little g, I don't mean the rapper out of Compton. I mean gravity, right? The acceleration due to gravity. So notice when I write the sentence, it's units on the independent variable, t equals 1 second to t equals 5 seconds. The average speed of the move is the falling and crying textbook is, and then I put units on the dependent variable, 96 feet per second. Okay? So there's your sentence. All right, that's good information to know, right? Part B. What is the average speed then on the interval from time equals A to time equals A plus H, assuming that the book is falling during that time interval? Go ahead, set it up. You're going to look at that and say, hey, there's a dearth of numbers here. A dearth of numbers. What does dearth mean? Dearth bigger. No. Dearth is an antonym to plethora. What is plethora? A lot. So dearth would mean a scarcity, right? Very few. We don't have numbers here, but is that okay? Yes, it is. Very good. Very good. Y'all said, well, it's okay. Y'all said something. Yeah, go ahead. Set it up the exact same way. These letters represent numbers. That's all they represent. I'll do it here with you. If you get stuck, you can just peek up. The average velocity is going to be the distance at A plus H minus the distance at A all over the change in the corresponding time values, A plus H minus A. I'm going to simplify that before I plug in, because something nice happens in the denominator. A plus H minus A is just H. Huh? Oh, yeah, T is this is another way to give the interval. So instead of saying, this is like our X, right? So for T equals 1 to 5, that's what A means, and this is just the other way to do it. We're just looking at this time interval. Another way to write that is on the interval from A to A plus H. T is our independent variable instead of X. Now, I want you to stare very closely at this until something comes to mind. If you stare long enough, you'll see like a breaching whale coming out of the ocean. What about narwhal? A narwhal as well, maybe. I don't know. Right? Have you ever tried those on those pictures? They're in the mall and they're all fuzzy, and if you stare at them long enough, something appears. I can never see that. Yeah, it's a boat. No, what emerges? What do you recognize that as? Who said Lamborghini? Quentin is back, everybody. Let's give him a round of applause. Quentin Pipes is here 2 days in a row, and he's participating. He sees a Lamborghini. Okay. Anybody who's taken, I don't know, any one of my last 2 tests, recognize that? Thank you. That is my favorite problem. The only difference is the function's name is D instead of F, and we're using A's instead of X's, right? But it's the exact same thing. Why is this my favorite problem? Not just because of all the delicious algebra that's involved, but it's related to, what does this give us? It gives us the average velocity between 2 arbitrary moments in time. Time A and the moment that is H units away, where H is some distance in time. So if A was 1 and H was 3, that would be from 1 to 4, right? If A was 5 and H was 10, that would be from 5 seconds to 15 seconds, so on and so forth. So this is how formulas originate, right? If you have physics, you're handed a formula sheet and you're like, here, use this. And you look at it and you're like, I don't know what to use when, where. You don't need formula charts if you embed the math as you go, and that's what we're doing. So let's go ahead and simplify it. A plus H, how are we going to evaluate that? We're going to plug it in right there for T. Now, is that 16A squared plus H? Is that how we do it? No, some people are still doing it that way. That's not substituting in. That's just adding an H at the end. That's going to be 16 times the quantity, A plus H squared, minus 16A squared, plugging it into 16T squared, all over H. So good so far? So far, so good? We practice this, we practice this, we practice this. This should be easy. Now we're going to expand it out. So you either go off to the side or you get on board with the ditty, right? Which is what? Not P ditty, but the ditty. Square, multiply double, and then square. Yeah, square, so that's A squared. Multiply them, you get AH, or A, if you pronounce it. Doubled, you get 2A plus H squared. Square, multiply double, square. And we still have minus 16A squared. It's still all over Herculean H. And now we distribute the 16, and we get 16A squared plus 32AH plus 16H squared minus 16A squared, all over Herculean H. And, of course, you've done this problem enough times. Some of y'all did it 9 times one night, remember? That if you set it up correctly and you expanded it correctly, great things should happen in the numerator. Namely, anything without an H should cancel. 16A squared minus 16A squared. And you notice the 2 terms that are left both have an H. So let's factor it out. We get H times 32A plus 16H all over H. And probably the most exciting part of the problem, what happens to the H's? Don't say cancel. They divide out. That one was weak. There we go. And we're left with 32A plus 16H. And of course, H can't be 0. Why can H not be 0? How many points do I have if H is 0? I'd have A as my starting X value and A plus 0, which is also A, as my ending value. Do I have an interval of time at all if I let H equal 0? No. So H can't be 0. And of course, if we would have plugged it in, we would have got 0 over 0, right? Before we divided it out, we got 0 over 0. But once we divide it out, we get 32A plus 16H, and this gives us the average velocity of the falling book for any time on the interval from T equals A to A plus H. Why would I want to do that? Well, a couple of reasons. Let's say I wanted to find the average velocity over several different intervals. I wouldn't want to have to set up the difference quotient each and every time and go through all of that plugging in, subtracting, dividing. That's exhausting. So I could do this with variables, come up with a handy-dandy formula at the end, and then evaluate it, which is now just a plug-and-play kind of thing. Just drop it in and evaluate instead of set it up and work through it. So let's verify example A. Let's verify example A. Verify example A. Okay, so on part A, what was the value that we were starting at? What would we have as our A value? 1, right? We started at 1. What is our H then? It's the span of time we allow to go by. How far is it from 1 second to 5 seconds? 4 seconds. So those are our 2 inputs. I'm starting at 1 second, and I'm going to let 4 seconds elapse. So this would be on the interval from 1 to 4 seconds later is 5. Everyone okay with that? All right. So now, instead of evaluating the difference quotient that way, since I just found my handy-dandy formula, let's plug it in. So the average velocity of the function, I'll just say, I'll just put from 1 to 5 here, is going to be, let's plug it in. That's going to be 32 times A, which is 32 times 1, plus 16 times H. What's H? 4. And now all I got to do is simplify that. That's 32 plus 4 times 16 is 64. And if I add those together, I get 96 feet per second. Is that the same thing we got on part A? It is. But now I can use that formula for other things. Like, let's say I want to know the average rate of change on the small interval. Let's say from 2 to 3. What is the average velocity of that function on the interval from 2 to 3? On your mark, set, go. You do it. I want to find the average velocity of the following book on that 1 second interval from t equals 2 to 3 seconds. Bonus problem. You don't have to use the difference quotient here. A 1 second interval is a very small interval. So finding the average velocity on a 1 second interval, that's pretty darn close to finding its instantaneous velocity at a given moment. Still worlds away, really, though, in terms of getting to what we call calculus. But this is what Galileo was doing. He wasn't dropping textbooks. He was rolling things down inclined planes. Squares didn't work well, so he went with spheres. All right, so for this problem, what is our A value if I'm going from 2 to 3? 2, it's our starting value. What is H? Is it 3? It's 1. We define H to be the change in time. It's the amount of time we let elapse. We're starting at 2, we're going for 1 second. So now we can plug it back into that handy-dandy formula. So the average velocity on that 1 second interval is 32 times A, which is 2, plus 16 times H, which is 1. And if I evaluate that, I get 64 plus 16, which is 80 feet per second. There you go. It's very hard to observe like Galileo did. He was trying to find the instantaneous rate of those spheres rolling down inclined planes. He wasn't actually there with like a stopwatch and a ruler, like going click and then click, measuring the two different heights. What he did is he did something like this. He observed things over a longer span, came up with an equation, and he was calculating things, okay? But here's the magic. Here's the magic. If I want to know how fast something is going at a single moment in time, I can't let h equal 0. But what if I took the limit as h approached 0? That would be the limit of this average velocity function. Now notice we've already divided the h over h out. See that? So we remember that if we plugged in a 0, we got 0 over 0, which means that this function has a what at h equals 0? A whole. Do we know how to find y values of wholes? We do. We factor out the thing that's causing 0 over 0, and then once it's gone, we can use, remember, whatever's left to figure out what the y value was. So we've already divided out the 0 over 0. So what if I plug in a 0 for h? What do I get? I get 32 times a plus 0. This now is the Holy Grail equation, because this no longer gives us the average velocity. This gives us the instantaneous velocity at time equals a. In fact, if you have been in physics, you know the velocity of a falling object is 32t, or negative 32t, or negative, it could also be negative 9.8t if you're using meters, okay? This is not velocity per se, because the sign is positive, but this is the speed function. This is the instantaneous speed function. So we just did calculus. Now, if you want to know how fast the book is falling in the beginning, right when we let it go, plug in a time equals 0. What's 0 times 32? 0. How fast was the book going exactly 1 second after we let it go? 32. How fast was it going 2 seconds after we let it go? 64. You get the idea. The acceleration due to gravity is 32 feet per second each second, or 9.8 meters per second each second. Do we know when the book hit the ground? We don't know when the book hit the ground, but let's say that the book fell for 4 minutes. Oh, no, not 4 minutes. Yeah, let's say the book fell for 4 seconds, okay? Can we find now how fast the book was going when it actually hit the ground? We can. We just let A equal that time. Or we moved it back to T. We find the speed function at 4 seconds. That's just 32 times 4, which is 128 feet per second. That's astounding. You just learned calculus today. I'm not going to hold you accountable for doing calculus, but I do want you to know why it's my favorite problem. Because it's the holy grail equation for calculus. It's what Leibniz and Newton discovered to help them answer questions. What is the slope of a tangent line? How do you find the slope of a line when the algebra requires 2 points and you only have 1? Or in Newton's case, how do you describe how fast something is moving in its orbit around a planet at a given moment in time if all you have is a picture of that planet moving in its orbit? How can you tell from a single instant in time how fast something's moving? This answers the question. My favorite problem sets up the discovery of what's called differential calculus. So that's why it's my favorite problem. All right, so for y'all, this is all I would expect y'all to do, is to be able to find that average rate of change function without taking the limit as h goes to 0 and evaluating it on a particular interval, okay? You want to do one more? Okay, let's use that one right there. We're still dropping the book. Let's find the average velocity. How much time do we got? Let's not do another one. We don't have time. Okay, so we've planted the seed there of calculus. Tomorrow we're going to work with symmetry, and then we should finish the notes tomorrow after the quiz. All right? Find average rate of change, difference quotient on the quiz tomorrow. Have a splendid National Taco / Golf Day.